Yeah, I guess the number is slowing down, so I might just get started. Yeah, hello everyone. Yeah, thanks for joining the seminar. For those of you who are attending this for the first time, the MP seminar series are co-organized by the Materials Project and the Materials Virtual Lab at UC San Diego. So we host monthly talks from top researchers in the field, focused on the topics of interest to the MP community. The examples include computational materials design, use of MP tools to perform research, and also recently the very hot topic machine learning applied to materials research. Because we have a relatively large audience, it's not possible for the speaker to answer them during the talk. So please use the Q&A button at the bottom to ask questions. And all those questions may be answered by the speaker after the talk. And for those of you who are watching a recording video, you can always feel free to ask questions at our forum. As I said, we have a recording, so those recording will be posted to a few locations a few days after the talk. We'll try to do this as soon as possible once the videos are ready. So the two locations are Materials Project Seminar website and the Materials Virtual Lab YouTube channel. We're still actively looking for speakers for the coming month. So for those who have your preferred researcher, please always let us know and we can try to contact them. Okay, for today, I'm very excited to have Dr. Artrith from Utrecht University. She will give us a talk about modeling of complex energy materials with machine learning. So before her talk, I'd like to spend 1 minute or so to introduce her to everyone. Dr. Nongnuch, Dr. Artrith is a tenure-track professor in the materials chemistry and catalysis group at the Dubai Institute of Nanomaterials Science. Prior to joining Utrecht University, she was a research scientist at Columbia University, USA, and also a PI in the Columbia Center for Computational Electrochemistry. She obtained her PhD in theoretical chemistry from Ruhr University, Bochum at Germany for the development of machine learning models for materials chemistry. She was awarded a Schellenberger Foundation Fellowship for postdoc research at MIT, and subsequently she joined UC Berkeley as an associate specialist. In 2019, she was named a Scialog Fellow for Advanced Energy Storage. She is the main developer for the open source machine learning package called Atomic Energy Net or AENet. I'm not sure if I say the name correctly, please correct me afterwards. For the atomistic simulation, her interests focus on the development and application of first principles and machine learning methods for computational discovery of energy materials and therefore the interpretation of experimental observations. Without further ado, let's welcome Nong for her talk. So I will pass the sharing to you.
Thank you so much for very nice and very kind introductions, Dr. Shi Chen. So this is my first slide. I hope you see the full screen, right? Okay, perfect. So hi everyone, thanks again for coming and join us today. So today I'm going to show or demonstrate how we do simulations or modelings of complex energy materials by using our machine learning models that we developed, and also we share with the scientific communities, the Atomic Energy Network, AENet. So when we develop our models, we always, after publications or after we publish, we always share the database and also machine learning models with the scientific community. So just briefly to give introductions, as you may know that many energy conversions processes are based on reactions at, for example, the interfaces that can be very complex and very challenging for first principle calculation or simulations. So here, this is a cartoon of electrocatalytic CO2 reductions. So to model such a complex process, we have to really find models that describe complicated phases such as liquid, solids, or interfaces. So this is really very challenging and difficult. For example, in these material projects communities, I guess that DFT is to discuss or to looking at such a complex system is really very difficult. And another example that I would like to show that many aspects of batteries are too complex for DFTs. So consider these two examples. On the left-hand side, you can see really very nice, beautiful STM figures by Dr. Datnis and also Dr. Meng's groups with the interface in solid-state batteries. So lithium cobalt oxide here near the interface is disorder, and also amorphous ligands at the electrolytes, also the anode. Or another example, this is a silicon anode. The figures from Professor Yi's face at Stanford. You can see that there are so many different phases here. So this structure really can be very important for the reactions. For example, we are interested in nano structures, particle size domains, and also interfaces, and also amorphous phases. So at Columbia, so the work that I'm going to present today is based on the previous work that I have been working before during the time at my postdoc at MIT, and also some work in the SEDA group in UC Berkeley, and also some preliminary results that I'm also part of the Columbia Center for Computational Electrochemistry here. So what we did, we combine atomistic simulations and machine learning to address, for example, complex system like the interface here, like in this complex battery structures, like you can see here. The general idea of how we really make use of machine learning. So the idea is that we use machine learning methods for representing the potential energy surface, or PES, from to describe the accurate energy methods, for example, from quantum mechanics database, or first principles, or accurate DFT methods, for example. And then we use machine learning models to interpolate and to construct continuous, efficient, and accurate potential energy potentials, machine learning potentials here. And then we use the accurate and efficient machine learning potentials in application to looking at, for example, large range and also long time scales. Accurate energies we can use in Monte Carlo simulation, and also accurate forces we can use in MD simulations. Our approach, we use artificial neural networks for the interpolation, because they can be very accurate and can be trained on large data sets with hundreds or thousands or millions of data points. And the models only just need or based on atomic positions, and we can construct a really reactive and also full dimensional. But to construct one machine learning potentials for real applications, it needs a lot of time and also take effort to construct and validate them before we can really use it in our intended applications. The idea to use neural potential to represent potential energy surface is not new. For example, here in 1995, Doreen and co-workers reported in JCP that they show for the first time that PES to represent neural potentials for nickel 111 surface and carbon monoxide molecules. And then in 2004, the Schaeffler group in Berlin show that they also can develop specify a neural potential to describe the PES for complex palladium 100 and in the environment of like potassium and hydrogen molecules. And then for the first time in 2007, Baylor and Pinello that show and demonstrates for first high-dimensional neural network potentials for any number of atoms, but they only show for single chemical species like a silicon. In this work, they use neural potential to describe many different phases, like also including complex phases in one potentials in the silicon structures. And then when I joined the Baylor group as a PhD student, together with the colleagues, we extended these methods to describe multi-component systems and also include long-range electrostatic interactions. We demonstrate the capabilities of multi-component system with the zinc oxides, and also looking at also charge transfer in zinc oxides. But then later in 2017 in the SEDA group, actually we're looking at the complexities of the battery materials. So for two chemical species, the model that described by Bella Paninello is not really enough. So we also extend the method for many more chemical species, but I also will show in this talk in details on the methods. And then later in 2017, Royberg also show really very big data set, like 5 million data points of organic molecules that show neural network potential can describe complex system of hydrogen, carbon, nitrogen, and oxygen. So as you can see that since 2011, neural potentials have become more and more popular. The number of publications per year is now growing really very fast. So I just searched neural potentials in the Google Scholars, and you can see that this is really many number of publications. But right now that not only just neural network potentials, there are many different keywords and terms like machine learning potential, also machine learning force field. So I include all of those keywords. You can see that really the publication really growing. And you also can see here, actually, even though there are many really publications, but many of the models that we can see from published paper not really ready to reuse for many different applications, but we still need to continue the development. So in brief, this is to show an example of a simple feed-forward neural network. So on the left-hand side, this neural network has 3 layers with artificial neurons or nodes. Like you can see here, the input layer and output layer, they have physical meanings. Input layer to represent atomic structures, and output layer, this is the application that we would like to have or predict. This is like energies or forces. So for our application, like you can see here, the atomic layer or atomic structure that we need. And in the hidden layer, this is just mathematics to describe the complexities of our neural network or machine learning models. So on the right-hand side, like you can see here, this is the same 3 layers neural network. The atomic forces can be calculated from analytic derivatives. So these equations for each node or artificial neurons of the neural network apply nonlinear. For example, we call activation functions. This example show the hyperbolic tangents. So simpler, I just demonstrate here the reference data as a parabola like x squared on the y-axis, and this is the x. This is that we would like to really fit this simple nonlinear parabola. So you can see this is the simple feed-forward neural network that as I described. This is the equations to have the neural network energies, like in the red curve here. So the black diamond shape, this is a parabola as a reference, and the blue for the first one, this is in this term. We apply one single node and also hyperbolic tangents, and combined with the second node here. This is the blue one, the green one. This is also apply hyperbolic tangents, and then sum up together with constant. This is the bias, and then it's shipped sum together with these 3 terms, and then shift to the right position of parabola curve. And neural network work the same like this. In realistic, it is not that simple, right? This is show high-dimensional neural networks. So to predict the energies of structures with any numbers of atoms. So Bella and Paninello already proposed in 2007 to train artificial neural network to predict atomic energies. For example, like here, I just showed already in the previous slides. So in these high-dimensional neural networks, the input for each single neural network is the description of, for example, the local environment we call here of the single atoms. This is like a fingerprint. So this structural fingerprints usually describe the local environment within a radius cutoff. So this is from my own experience. I'm only looking at like a condensed materials. 6 to 8 angstroms is already good enough to describe. Because this is the atomic position that you are familiar with, like a XYZ coordinate. So to make it more invariant and can later use in neural network models. So we have to convert the number of atomic position as a local environment. So I will also discuss this in the next few slides, why it is so important in this. So for example, the properties of atomic energies, right? The descriptors has to follow the invariance of energies. In these equations, you can see here total energies of structures like sigma is the sum of atomic energies. And the atomic energies have to follow the physical invariance of total energies. The atomic energies have to be also invariant with respect to exchange of equivalent atoms and with respect to translation and also rotation of the structures, like you can see the cartoon here. So more details also discussed in these two publications. So additionally, the descriptors need to be constant with length. So each neural network has one specific number of input nodes. So therefore, the length of the atomic structures descriptor has to be constant. The size of descriptor also has to be independent of number of atoms and also chemical species in the structures. We made, for example, a wish list of descriptor of local atomic environments. Like you can see here, a few points. The input or descriptors are important, right? So the descriptor should be automatically and should not require many tunable parameters. Its accuracy should be systematically improvable. It should be as efficient as possible. This is very important. And its computational cost should not depending on also number of complex of the chemical species in the structures. So this is what we propose to describe our atomic or local atomic environments here. So the descriptor of local atomic environments, the fingerprints or the descriptor. So we use it based on an expansions of the local radial distribution functions or RDF and angular distribution functions ADF here. This is described in the basis of Chebyshev polynomials or Chebyshev expansions. Here in A and C figures that I draw as a cartoon, the alpha, like you can see here, alpha is the Chebyshev polynomials of order defined alpha. Defined, this is the Chebyshev polynomials in order of the alpha. And C alpha is corresponding to expansion coefficients. And the local atomic structures, like you can see here, with the coordinates of all atoms within RC or R cut, we describe two sets of coefficients. So one set is the bond length, like RDF, and another is the bond angle, is ADF, like you can see here. So this is the descriptor that we use to describe structures. And now is how about many different types of chemical species? So we introduce a second set of like weight coefficients that use in the way that to capture the local compositions or atom types or chemical species. So in the notation here, I use W's or T or weight type of chemical species. If you have one chemical species in your system, so we have 0 as a weight. So then you only need to describe only the structure only on the top. But if you have 2 chemical species, so the weight type that we apply is -1 or +1. If you have 3 type of chemical species, you can use like a -1, 0, and +1, for example. And so maybe describe as a cartoon is not that easy to understand. Sometimes it's easier to look at equations than just the cartoon that I just showed before. Here are the equations of the Chebyshev descriptors for the local chemical species or atom type T that I just discussed before. The descriptors components are the expansion coefficients of the RDF and ADF, and the weights or WTJ, like you can see here, are specific for the atomic species. So the descriptor for the local structures, if it's equivalent, so all other weights are equal to 1, for example, like you can see here. So we do, or we did some tests or showed, this slide showed the benchmark of the Chebyshev descriptor that can be used for any numbers of chemical species with the same accuracies and also high, with the same efficiencies and also high accuracy, like you can see here. So in B figures, so we take the database from the material projects and we test our descriptors. The x-axis is the descriptor dimensions, like you can see here, from 10s until like a 90s. And the y-axis, this is show the root mean squares, RMSE, that neural network potentials predicts the accuracies reference data as DFT. So we test with many different chemical species that the data that we extract from the material project. This is the lithium potential metal oxide rock salt structures that we contain many different chemical species, 3 chemical species, 4, 5, and 11 chemical species, like you can see here. So most of them really show the numeric predictions, the errors really low. In this case, we already have the convert at the 3 millieV per atom. And also the same type of the Chebyshev polynomial descriptors, we also take the database from Nomad. The data I take is a complex amino acids from ABCM's code. There are around 60K data points that contain 5 chemical species and also 11 chemical species that I take it as a benchmark. So both systems for crystal structures and molecular system, our Chebyshev polynomial descriptor can describe accurate neural potentials like you can see here. This is an example of neural training. We can train a neural network potentials on reference data. For example, in this case, I show water dimer. The diamond shape show DFT, and neural network represent here in the solid line in red color. And another complex system, this is a copper gold crystal structures. There are many different compositions. For example, gold 1, copper 3, gold 2, copper 2, and gold 3, copper 1. So after a few iterations, like you can see here, after training, neural potentials can predict the reference DFT data really accurately. So this show, or this conclusion, the conclusion showed that neural network can really establish a functional relationship between the structures and its energies. So far, I only show you neural networks training only the structures and energies already. So a few years ago, we also thought that, okay, using the force information from reference data, for example, audit also provide from the FT, this could be useful. But using all information from the forces, it can be really very expensive. So we decided maybe we can try something. Maybe we looking at more efficient methods. So what we did, we proposed an efficient approach for training neural potential, including atomic forces via Taylor expansion. So just in brief, like you can see here, 2 graphs that I show how we're looking at the absolute forces. In the x-axis on the figure on the left, you can see the errors in absolute forces. In this case, we're looking at the water 6 molecules. The data set that we have like 3 data sets, like 500 structures, 1,000 structures, 2,000 structures. You can see clearly, like if we have many more structures in the training sets, right, the absolute forces with accuracy is quite good. And when we have a really small number of structures in the training set and only use energy fitting only, you can see that the errors is really very high or really large force errors. And also here looking at it's the tail is really going spread when you have less data points. And also when you have more data points, you can see that the forces is really accurate. But in realistics, that we cannot generate a lot of data points easily in the same time. That's why using our methods maybe could help. So we demonstrate, for example, here, just show you, we develop an efficient approximation force training approach. So we use a Taylor expansion to estimate the energies of structures with, for example, small displaced atoms, like you can see here in these equations. So I can show you how it's worked. In the left-hand side, energy fitting only. The gray curve, this is the potential energy surface that we would like to describe for carbon dimer. And the example of DFT data points, just in blue, we have only 7 data points. And then we use these 7 data points and train neural potentials. You can see that it's only just predict almost right, but it's still wrong structures and also wrong the energies. But then we introduce more data points, use the Taylor expansion method and approximation. We introduce a few more data points. In this case, we introduce small atomic displacements like minus x and plus x, and we introduce more data points, and then we train neural potentials. It's improved the predictions, you can see it's get right atomic structures and also get right energies. So we also test what the distances that we should use and introduce in each structures. In this case, the data generation for water 6 molecules in these structures, and there are so many different data points in the training set. So what we did, so we randomed atomic displacements and vary from very small distances until we find that what could be the best distance that can apply to a water system here. So you can see here that introduce 0.01 angstrom give the best results that we can look at the mean absolute errors of atomic forces, the best performance. And in the same time that introduce number of atoms of the structures to include in the training set. So more structures also give better results, give good force predictions too. And in realistic, you can see that want to see why don't we just use directly the force training, because it look here in the black color in the plot here, using direct forces in the training methods or training process. It gives very good accuracies, you can see here. But even in these simple 6 water molecules or water cluster here, it take like 8 times more CPU time than our methods Taylor expansions. So in realistic, like in isolate or molecular system, I think this works well, or it works okay. But my work mainly only the complex condensed periodic structures, and use direct for training is just not really easy, and it takes very much a CPU time. I can show you one example of our benchmark. So we look at inorganic solids cathode batteries. In these compositions have like 5 chemical species. It's also, again, this is the rock salt structures. You can see here, we also did the same test. We also try to find what is the best distances that we can introduce, and also estimate the energies after we have the Taylor expansions. So we see that in the solid structure that we have 0.02 angstroms introduced and include force information in the training set. It's really also improve our neural potentials. So after construct example as a benchmark of neural potentials, we use only 800 reference DFT structures that we develop, and then we apply the force information or include force information by Taylor expansions in the training set. And you see that neural potentials use the information from Taylor expansions, improve the stabilities of long MD simulations even in 1 nanosecond. But then look back, only use 800 structures, only DFT energies that you use in the training set, and then you use in the applications and train, and then run MD1s. You can see it's really not really equilibrate and also fluctuate very much. And then in the second MD simulation, use also just 800 structures and 800 energies, and it's suddenly like in MD simulation, it just explodes. So this is the demonstration to show that include our new approach to include force information where Taylor expansion improve the MD simulation, it make it more stable. But note that this is just a benchmark. You cannot use these 800 atomic structures and then use in the real application. So in real application, you need even to add more structures and try to really find what can be really used in your own application. For example, here, this is the diagram that we propose, how we really can construct one neural potentials in practice. So usually we construct neural potentials in a way like an iterative refinement or iterative process. For example, we have a database, especially we make use of the material projects that already provide many different types of crystal structures that we can really start to use it as initial data. And then we can select what can be data that we can really use in our own application. And then in the process of select models like neural potential, there are so many hyperparameters that we have to train and test and validate. If it in the validation is not good, we always have to do it again and again, iterative refinements. And when we think this is already good, then we can use to real test in our application if it doesn't really work. So we have to really integrate also other types of method, which is active learning, so that we can find and make sure that we get more or good configurations that cover or complete our full potential energy surface. So we do this again and again. Maybe this diagram is quite abstract. I would like to show you more concrete examples. And if you are interested in, we also provide how to use with the Jupyter notebook together with Google Colab, so you can play around with this full construct potential energy surface in practice. So basically, we have the initial reference data, and then we construct the preliminary neural potentials, and then we use in MD simulations, and then we check, use the neural potential to predict if it really give in good agreements with the reference method or not. You can see that O is quite really large between neural network potential that predict quite large errors with the reference method. So we can really do it again by include them back in the data sets and then refine it until it's really have really a low RMSE or the errors. But of course, even we have very low RMSE, it doesn't mean that this neural potential is already really ready to use for your own application. We have to also validate with many other methods, like for example, more accurate methods, or even compare with experimental measurement, for example. So basically, this is the overview of our workflows. We have the our initial data, and then we start to construct, and then we do this again and again, iterative refinements. And once we have it, we also share our models in like some open repositories, and then we can also share with the scientific communities, like you can see here. If you have your own application, which is not really can easily use from the share potentials, you can also further refine with your own application with the new data. It's easily just to add more data points and then retrain and refit. So this is the benefit of how to use neural potentials in your own application. So basically, most of the methods or the new approach that I mentioned is implemented in our open and free atomic energy networks software package. We also not only have its own just to predict accurate energy or forces, we also provide any libraries that can use also with other open software package, for example, ASE, LAM, Tinker, or DL Poly, or even the genetic algorithms. So you can check or look at our manuscript here. Just in brief, to show you that ANET also can really use or compatible with many high-performance computing architectures or systems. So together with Professor Urban and Columbia, so we really test and use with many different HPC systems. For example, when I was in Berkeley, we also test and use in the US DOE on NERNs, and also NSF Exceeds, also DOE computers at the Brookhaven National Labs, also at Columbia High-Performance Computing, Terremoto, Skinwork. And right now we also test and try on the NWs on Surf-Sahara in the Netherlands. So together with many scientists, and it also still need more and more help to improve or to even extend more for different applications, including also we try also to compatible with a GPU, for example. So we are also looking for collaborators if you are interested in. So right now, I also have to say thanks to, for example, the Taylor expansions, April, and together with Professor Kaisner from Stuttgart, and also the compatible with LAMPS, so Dr. Molowitz, Michael Chen, and Professor Markland, and also Dr. Moritz from Stanford, really have to implement it. Just briefly to show as a benchmark here, it shows really our ANET is really highly parallel. In this case, we show the test 1 million atoms. It takes only just 50 seconds for this is just N10 MD steps on 96 CPU cores on the Columbia supercomputers here. So you can see that you can use many different cores. It's really very efficient if you use many nodes in your own high performance computing or computers in your own situation, I mean, in your universities. And it's only lost around 20% if you really want to use for your application and use many nodes or many cores. But in realistic, your own application, you don't need to run like 1 million of atoms, right? Maybe like a few thousand of atoms for a complex system, or even 10K of atoms. So we really take much less CPU costs. So you can try even on your own laptop once you already construct and have really efficient and accurate neural potentials. So this is just to show benchmark. Let's see if I have enough time, I would like to demonstrate how neural potentials can use to describe complex energy materials. I will not discuss too much about science inside because you can follow my publications, but I just want to demonstrate how we can make use of neural potentials in many different applications. For example, here, over the years, we investigate different research questions in energy conversions and also energy storage. For example, in catalysis, we investigated metal support interactions, solvent effects, and also active sites in oxides. In battery, we simulated the structures and also lithium transport in amorphous and also nanostructures phases, like I just showed you before. This is a show a few lists of publications that we really demonstrate and use a machine learning potential. So the list here listed based on my own work. So some of other scientists also make use of ANET and also publish their own work here. We are really happy to support and also to help you to get started if you are interested in. We have ANET website and ANET forums. If you're interested, and we are happy to help you to get started. So let's see some example. So back in the Baylor group, in 2013, we investigated for example, copper cluster as zinc oxide catalyst for methanol synthesis. The system in this system exhibits really strong metal support interactions, and our experimental collaborators were looking for an explanation for their observation, for example, here. So zinc oxide supported copper is a catalyst for methanol synthesis, right? Actually, it is known that the copper form, shape, change is really different on the environments, like the gas exposed in the synthesis condition, for example. So we use machine learning potentials or neural potentials to simulate a copper nanoparticles on zinc oxide with around 8,000 atoms in total, like you can see here. So actually, this would not have been possible with only the FT methods. So our simulation showed that the copper clusters sink into the zinc oxide surface and form a pyramidal shape, like you can see here. This is also in agreement with the STM images from our collaborators. And another example that I would like to briefly show you how we modeling of nano structures catalysis system. For example, here, copper gold nanoalloys are efficient and stable catalysts for oxygen reaction, for example, also CO2 reductions. So actually copper itself is a good catalyst, but oxidize too fast in the reactors, like you can see here, only the light blue here, it really stopped in the reactors really very short time. But once Professor Yang Xiaohong, this is the images from the Xiaohong lab at MIT, they demonstrate that mixed with a gold, so it's also helped to make the reaction stay longer or stable. But the system of the cluster size is around 5 to 10 nanometer cluster size. So as computational material scientists, how can we help to identify the important compositions or the surface structures? So what we did, we again developed neural potentials of copper golds. And then we first look at copper gold nanoparticles in vacuums. And then we used and with Monte Carlo simulations to investigate, for example, the atomic orderings of copper and gold atoms, like you can see here. So we see that the gold, the yellow, and the copper atoms, orange here, rearranged in core shell orderings in small nanoparticles, in this case up to 4 nanometer cluster size, which is around 1,000 atoms. So in vacuum, gold prefers to be at the particle surface, like you can see here. And then take a look at with DFT calculations if we would do this simulation with 147 atoms. So it will take around 3 hours at the 16 cores. Of course, this work is done in 2014. I know that now you have much better computers, but just to keep this as to consist with my time and my year. But with neural potential that we developed, it takes just 1 second on my laptop. It's just 1 core that you can see here. And now realistic nanoparticles or cluster size around 4,000 atoms with DFT is very, very difficult. And with neural potential that we have, it takes like 1 minute to predict such these compositions. And we also can use neural potential that we developed to samplings and many different compositions and find how many percentage like a gold chemical potential or copper chemical potentials, and can also use it in MD simulation like you can see here. So this is just to show and demonstrate that once we can develop efficient and accurate neural potentials, we can do a lot of simulation and to really help to accelerate our research in this direction. And not only that, we could also extend our database by including, for example, in this case, we have a copper in solutions. So we include more chemical species like water to demonstrate that it also can simulate nanoparticle in solution. You can see that there are so many different compositions, and the output after we do simulation also show different results from in vacuum. So this really show that realistic conditions also very important, right, in your simulations. As I mentioned earlier, I don't want to discuss about science, our finding here, but just want to demonstrate how our neural potential can use in your complex research and can help to accelerate the simulations. Another example, again, together with Professor Yang Xiaohong. So one of the students, so now he's Dr. Elias just come, oh no, can you please help me to find where copper atom sits in the serial oxide nanoparticle here? Because of in the experiment that we see in this image, everything only gray and white and black here. I don't know where the copper sits. So we just perform in potentials and use it again in Monte Carlo simulations for the cluster size around 3.5 nanoparticles with around 1,300 atoms to understand where the copper atoms really insert and sit in the serial oxide here. So we really looking at, so in this movie, copper in blue, serial is pink and oxygen is red. So, but in the picture here, so sorry that this is not consistent. So copper is in orange in this figure. So we really can help our experimental collaborators find where a copper atom sits. And when we see already where the structure and how atomic look like, and then we take from the model or the phases, and then looking at and find and use the DFT calculations to help to find this could be the most stable in the structures, and then we can use the DFT to find the oxidation state, which is where the active sites. So this is also very useful, use neural potential to help to find the active sites of the structures. Another example, you can see that amorphous like a silicon anode that I show here. This works together with the Zeta groups, Professor Zeta. So in general, the silicon anode is really very challenging system to model because of the amorphous silicon alloy phases, right? So we train neural potentials to reproduce all of the silicons, lithium silicon across its crystal structures here, and also amorphous here when the battery is cycling. So we remove lithium atoms and then see how the structure is really look like. And here we show the computed the phase diagram that really can remove a lot of lithium structures, and then we find what is the most stable structures. So this is how we computed use our neural potentials. But in this case, I only show the FG results because of neural network predicts as good as DFT. And also, we also compare our predictions of different phases with the experimental voltage profile. So our neural potentials also predict also good agreement with experimental voltage profile here. And then we also validate our neural potentials for lithium lithium diffusion parts. As you can see here, the agreement between neural potentials and DFT is excellent in many different channels and also different lithium concentrations in the structures. And not only that, we also check how good of the forces that we can use it in long MD simulations. In this case, I demonstrate only 2 nanoseconds, like you can see here. So many different compositions. This is just use one neural potentials, but can describe really many different compositions. Like you can see many different lithium concentrations. So all neural potentials can predict really, excellent and good agreement with the FT reference data. And we use neural potentials in the simulation with many different types of structures, nanoparticles, and many different phases in the structures, and also many different temperatures. And then later we predict the diffusities using the Arrhenius plots, and then convert to looking at like conductivities and also activation energies. And here, this table summary our predictions of 4 different compositions of lithium in the structures. And in the same time, as I already mentioned before, we also compare with the experimental measurements as a reference here. So our predictions also predict in good agreements of the order that experimental measurements also show here in different methods. So right now, or currently, we also work on develop neural potentials in many different systems. So we also got funded from the DOE-WTO, sorry, yeah, since 2019, and it will end in 2022. So I'm still in the collaborations and working together with the scientists at Columbia and also BNL. So we're looking at how rearrange of NMCs in different compositions, and also looking at the solid state LPS. This is a solid electrolyte. So there are so many different phases of the crystal structures, but during the battery cycling, the LPS also change to become amorphous. And also with Annika Stuckers, the postdoc at the CCDE. So we're also looking at how lithium anodes interact at interface with the ethylene carbonates or ECs. If I have time, I would like to take a really preliminary results of our neural potential for EC molecules on the lithium anode. Just really take a look. So we take a look at the phase diagram. This is also download from material projects, and we're looking at, there are so many different component and composition that we could look at and consider in the system. This is the phase diagram, and we construct, or we get the structures from material project, looking at bulk structures, and also later construct the surface models, and also derive the potentials with the clusters, like you can see here. And we really looking at many different compositions because they can also different local environments, like I just showed before. And really, there are so many different types of structure and composition that we really include in our database. So you can see here that there are so many different types because of how to use our data and structures. In the training set, there are so many different cluster size, and also in MD simulation, like you can see here. So what we did, we have the structures, and then we take a look and have like a central atom, like it can be lithium, oxygen, or carbon, and then get the structures as a cluster with different radius cutoff, 3 angstrom, 4, 5, 6. So you will have different, and the type of the structures, we can do either SCF calculations or geometry optimization or MD simulation, like I can show you here before. And now this is just a preliminary results and benchmark only the neural potential for lithium only. So we have only the bulk structures that contain only lithium FCC and BCC, and this is the qualities of our neural potentials. It's very kind of like a good agreement. This is on the black. This is the training data points. On the red, this is validate set. It looks very good. And then we use our neural potentials to predict, for example, the experimentals for non-dispersions. You can see the points, like you can see here, orange and red or blue here. This is the point from experimentals for non-dispersions. And our neural potential predicts, this is really kind of nicely mapped and over to the experimental measurements is nicely. So this is just a preliminary results that I would like to show you, just to take a look. But we still, this project is still ongoing, and right now we generate more and more the interface structures and data points that we can really then later use as a training set, and then construct neural potentials. So this is just, for example, we find where the most stable structures of EC molecules and also some system, for example, like oxygen molecules, on, for example, in this case, like a graphite is also in the structure that could also include in the training set. And we use Bayesian optimization structure search, or BOSS. This is developed from Professor Ringers from Artrith. And we see that there are so many different types of structures, and most of the structure and search we really can use in the training set. And also at the same time, we also develop the same method and use it with the EC molecules and also many other EC molecules that we are looking at on the first example, lithium 100. So this is just my last slides that I have. So I hope that today I could demonstrate that using force training approach and also the size of the reference data sets can be smaller since more pieces of information per structures are used in the training set. So this means less actual DFT calculation are needed. This also makes it easier to construct the preliminary neural potentials, for example, used in MD simulations. And then training on small data sets actually already produce quite nice or good or stable neural potentials, like I demonstrated before in the slides on the cathode complex 5 chemical species, like I just showed you before. And then in summary, so I hope that you can see that using neural potential or our machine learning potentials can really make it possible to simulate complex energy materials. And not only just to show and compare with your reference data, actually it is also very important that to validate your predictions from your machine learning models with many different sources. For example, maybe you could also looking at like the compare with the more accurate methods, like more accurate first principle data or even data from experiments. And one last point before I really finish my talk. So I think that machine learning model or machine learning potentials in material science is really rapidly growing, and also to really support and to help the communities, especially to have everybody can reproduce the data. I think it is nice that we provide or we have like a open science or open tools like material projects, and we really make use of, I mean, all the time, like a daily life, we use material projects data, and also the tool like PyMagents is really very helpful for everyone. I mean, for scientists who really can make use of these tools and the database. And we also have the same spirit. So we also develop our own init package, including more features, and we also will share with the scientific communities. So before I really close, I would like to also thank my collaborators and also facilities from the talk that I just presented today. Chen Wang, visiting PhD students, and also Dr. Hao Yugo, who work on batteries materials with the DOE VTO projects, and April Cooper, who helped to develop the force information, the Taylor expansion, and also of course, the discussion with Dr. Urbans, Dr. Hyberson at BNL, and also Dr. Chen at Columbia. And also Annika Stuckers, who provide the result and also information and work on the EC on the lithium anodes. I also would like to thank the support from Department of Energies and also the computer clusters from Exit, and also thanks computers resources from CF and Brookhaven National Labs. And of course, thank you very much for your attention. I'm happy to take questions.
Yeah, thank you for the wonderful talk. We do have a few, like 7 questions in the Q&A panel. Could you access it?
Actually, no, I cannot, but I will try to see. Okay, will the slides be shared following the webinars? You can contact me. I'm happy to share if you are interested in. But actually, when you have the talk, you could also follow the slides from the video, right? But I don't know, but I'm happy to share my slides.
I'm sorry to interrupt. There's a second Q&A panel, so I think
Yeah.
there are about 7 questions.
Oh. Could you please help to read question? Because I only can see the chat between us, I think.
Yeah, the first question is from Dioma, and he or she is asking how can he or she collaborate with you using this method on heterostructural composite materials that demand many investigation to determine the composition of the surface.
How to collaborate with me?
Yeah, yes.
Please contact me. I can give you my email address. I think the first slides that I have here, this is my email address. Or you can contact also any forums, and we can start to chat there. Also fine.
The second question is from Mahesh. He or she is asking if they can use these potentials for praseodymium nickel oxide system.
So this one, right? The one that I demonstrate for 5 chemical species here. As I mentioned before, we have to find the application first. This 800 structure here just to use to demonstrate my approach, my Taylor expansion methods. So the answer is I don't think so. We cannot use it for application.
But they need to like retrain the model.
That's right.
In this new system, right? And then I think you already have the software and the package. Those are really user-friendly, and the new users can just use their own training data to generate a new potential for the new system. Yeah.
That's right. So I just demonstrate this, how to use everything in the on Monday that I joined the Psyche machine learning into atomic potential workshops. So I have all the steps how to use everything here also on the deep note. If you are interested in to access all of the steps and also provide database, you can also contact me again.
Yeah. Another question from Felix. They're asking, have you evaluated the luminescence mechanism, and can the luminescence center be detected with this method?
Maybe I don't understand the question.
Oh, I think they are asking a property prediction, in my understanding, like predicting the luminescence center for the material, I guess. I guess that belongs to a different category of models, right?
That's correct. Yeah, sorry, I don't understand this. Maybe our neuropotentials don't do this. I mean, in this presentation, I don't talk about this. Sorry.
Yeah, but I guess if you are using the descriptors from the neural network potential, you can potentially couple the descriptor with the machine learning model to do a property prediction.
Yeah, that's right. Yeah.
So another question from Renee. With your machine learning approach, is it possible to determine with grand canonical simulations the distribution of charge carriers, such as lithium, in electrodes for externally applied voltages?
Yeah, this is a good question. We haven't have this kind of chart model yet, but together with showing the scientists, we are working on this application. So especially the last application that I just show, Annika and Turing's team, they are looking at those type of application here. So right now, our model cannot describe that, but we are working on it.
Yeah, nice. Question from Mingjian Wen. And first, he thanks Nong for the nice talk. Any comments on how to apply such potentials to electrochemical system like a battery? In such systems, species are charged particles, and electrodes can have varied electrochemical potential that depends on its charging state.
So I guess that like this example, is that correct? Yeah, I think this is what I demonstrate, that we can use efficient and accurate neural potentials to sampling many different state of charge. Yeah, and then we can also predict the voltage profile, like you can see here. But in this case, I just made it quite a few compositions that compare with like a high phases that 415 degrees Celsius that try to predict. So this is what we, yes, the answer is yes, we can use it to predict the voltage profile.
Nice. I actually have a similar question as when Minjian's. I'm wondering how can we simulate the charge transfer, the reaction happening in the battery system? Do we need to modify the formalism to include the charges, the varying charges, or we can use the existing framework?
I think we should modify the framework. Yeah, what I have is right now I'm confident with the system that I have. I think you mean like a long range interaction, also electrostatics, and looking at charge transfer. So in this model that I use, is that we don't include those type of properties in these models. But what I did with Professor Beller's, like a zinc oxide, we include a long range electrostatic term. We include the second set of neural potentials models to discuss or to describe that. We did demonstrate at the zinc oxide system.
I see.
But what I worked at MIT and also in Berkeley, so I didn't include those information. I mean, the information that I just mentioned before. Yeah.
Another participant asked if we have references, lectures, or courses for beginners. I guess your upcoming workshop or the tutorial section will help, right?
That's right. Actually, already happened, but we have also a video and also share with many others who could not join workshop. But if you want, also you can also take a look our paper here. In these demonstrations, we have really like GitHub atomistic.net MLP beginners guides. So I'm happy to share this link. Yeah. If you are interested in, just contact me. I'm happy to point to this GitHub repository. Yeah,
or maybe the participants can ask the question in the forum, the material science org forum. Maybe that some others can help out. So we have a question for anonymous attendee. Have you ever calculated a more complex material such as a ternary metal sulfide?
The sulfide? No, I haven't done my work. My work not related to that. So this is only the work that I have been working on, and no, I don't have that experience on that work. But we are currently working on the amorphous electrolyzer LPS right now, and we also use some of the how to say neural potentials, also looking at amorphous lipons to describe and how to dope the nitrogen in the Li3PO4 in the structure, and how to look at like the phase diagram when we increase the number of or the fluctuations of nitrogen in the structures. So this is what we work together with Dr. Lasevita. She's now in Samsung.
Yeah, I guess since you already have oxygen, right? The oxides, the sulfides are similar. And probably if the user want to use it, they can learn how to use AENet and then do the potential themselves. Should be doable, I guess.
That's right. You can reuse our descriptors again, but you need to provide atomic structures and also the energies of forces that you still need to provide the reference data. So I think the main challenge is that we need to have a good reference or enough or the database that cover potential energy surface on your applications, on your intended applications, right? The descriptor or machine learning model that we have with the cluster, how to say that Shape expansions, I would say that this is ready to use for any type of materials, but we still need to provide atomic structures and also that's related to the energies and also forces or even charges and many other information that we can really use it to develop your models. So
the next question, many thanks for the nice talk, Professor Artrith. I have a question regarding the choice of training data. one can imagine a situation where training examples with separate distances much smaller than the equilibrium separation. And they can have energies that can deviate strongly from DFT energies. In the probed region, the energy should scale exponentially. How do you avoid the situation where such energy offsets dominate the cost function and reduce the description around the equilibrium configuration?
So, okay, I'm not sure if I understood the questions. So,
yeah,
I mean,
those regions.
If we have the structure, I think those structure, especially short distance with high energy, is very important that to include in the training set, because this is to help to prevent that if during your MD simulation, often that it also can come very close or the short distances. If you don't have this structure in the training set, your MD simulation again can explode because of neural potentials or neural networks. There is no real capabilities of extrapolations, you know. So we have to really provide data or information that in the training set. So at least it should be seen. But again, we only provide the small number, I have to say, the data in the training set, only small structure, like one or even 100 atoms or 200 atoms that you can do the DFT calculations. But the big thing that we can really have is this, we can then use it in application for larger system. This is to see how the complexities that you really can achieve later. So the short distance also very important to include in the training set.
Yeah, definitely. The last question is, thank you for the wonderful talk. Could you comment on the neural network beyond the DFT accuracy? What would be the next steps? Smiling face, thanks.
The next step.
Yeah.
Actually, we have the models that, again, it's really depending on application, right? If you want to use it in Monte Carlo simulation, we can really provide very accurate, for example, the energies or forces already. But what is this, how to say it, I demonstrate already with many different cases, but what is this really big thing that maybe we could also include also some more physics to make it easier for example, like a transferable, because of right now, the main problem that we don't have enough reference data points to cover full potential energy surface. That's why I'm saying like, how can we really get the big data of neural potentials can really cover full potential energy surface? Or how can we develop such a model like, for example, like one oxygen neural potentials that can use it in any compositions, even different type of structures? Or we develop like a neural potentials of atomic potential, like a nickel, for example. It can also use in nickel composition, like a nickel 2+, nickel 3+, or nickel 4+. That would be really fantastic. So this is still in my head. How can we really develop neural networks for each chemical species that can be also used in many different compositions just one time? But I believe that maybe a large database and also really will also help to cover those kind of challenges. So there are many things, many things that we should really try to work on it, and let's see if it's work or not. Need to again validate, test, check, and benchmark, and and try for the real applications, right?
Yeah, very nice. If we are able to have a like element-based potential, then essentially this will replace the pseudo potential we use in TFT. That would be fantastic. Thank you very much for all these answers.
No, we don't want to replace the no, we cannot say this because of again, it's depending on your research area, right? We don't want to have neural potentials to replace DFT. We only want to do what we want to do. Like I always keep saying all the time, like okay, my application or my domains always talking about like a Monte Carlo simulation or MD simulation. This is what I'm confident with that. But if we would like to look at like electronics properties, very accurate, I still think like a more accurate methods or models like a DFT or even higher accuracy methods. That's still, we need all kind of methods, but we have to put the right methods to the right research questions. Sorry to say that we cannot replace each other.
Yeah, unfortunately, we don't have enough time for you to go through your other work on the DFT calculations. Otherwise, we'll be very happy to to see that too. Yeah, thanks again for attending the seminar for this wonderful talk. I guess we are running across our time, and thanks again for going to the length of answering all these questions. Thank you.
Thanks so much for the kind invitation. Thanks everyone for joining us today.
Thank you. Take care. Bye-bye.
Bye.